In this video, we will be discussing exponential growth and decay. When we talk about exponential growth and decay, exponential growth means that we have something that is starting out slowly, but then over a period of time it explodes. And so what we mean by explode is that it grows rapidly as time continues. So this first graph that we're looking at is a great example of growth. Now on the other side is a great example of decay, and that means that our number of items is decreasing over time, and then as that time progresses, it is slowing down its process of decreasing. And so that means that we have a decay. So this graph over to this side would be a decay. Now, some real-life applications of exponential growth and decay. Well, of growth, you could think about money in an investment, because a lot of times when you first invest, you will grow rapidly over time. And then you also could talk about population. Would be another good example. And then let's see, what else could we talk about? We could also talk about maybe antiques over a period of time, depending on what it is. So there's a lot of things that if it grows with value over a period of time, that's going to be a growth. Now for decay, a lot of times in science you talk about half-lives, and that would be a decay. It's a way of looking at elements, so half-life of elements. Also new car value. Let me slide this over. So anything you see that's going to decline in value, then you're going to have a decay. Now you've got two formulas that you need to make sure you know, forwards, backwards, any way possible. And in those, notice that there's a lot of different values inside of all of these formulas, and you need to know what each part implies. So make sure you understand where each part is coming from. And especially down here for time, time will be the x variable. When we graph some of these and we're looking in our calculator for particular values, t will be your x variable. And your new population, new growth, new decay, all of that is going to be your y variable in the calculators. So very important for you to remember that. Also, the rate of change that we're talking about is a decimal that is greater than 0. So do make sure you keep up with that. N, that's the number of periods it takes for the rate to occur. And of course, P sub 0, that's just going to be your initial population or initial amount that you have. Okay, our first example of a growth and decay problem. The very first example here, you need to assume that the number of bacteria in a bacterial culture doubles every hour, and that there are 1,000 bacteria present initially. So here they're asking us to fill in what our variables would be. And so our P sub 0, remember that's our initial population. Well, starting out, it said we had 1,000 bacteria present. And our rate, it is doubling every hour. So that's going to be 100% since it's doubling every hour. And so it's changing 100%. And then our N, remember, is the number of time periods it takes for this particular rate to occur. And so the number is saying that it doubles every hour, so one time period. Okay, so there's our variables. Now they want us to fill in, and here notice that the bacteria is doubling every hour, so this would be an exponential growth. So the formula we would use would be our population is going to be equal to, and our initial population, which is 1,000, times And again, we had 1 plus our rate. Well, 100%, if we change that back over to a decimal, it's just going to be 1. And then it's time period, or time divided by the number of time periods needed. So it's really our time divided by 1, which is just our time. And so we could simplify this equation to be 1,000 times 2 raised to our time. So that's going to be our equation we're going to be using to answer the next few questions. Now, as far as drawing a graph to represent, let's see, the bacteria present in the first 12 hours, this would be a growth. So we would use our calculators here, but just to get the idea, this would be an exponential growth. So it would look something like that. Now, how many bacteria are present after 8 hours and 15 minutes? Now, we are going to use our formula, so just a quick reminder of that formula. Our population is equal to 1,000 times 2 raised to our time period. And our time period was in hours. So we need to see 8 hours and 15 minutes, how many total hours that would be. So very quickly, we see that if we have 8 hours and 15 minutes, that's 15 over 60, which is going to be 8 1/4. And that as an improper fraction is going to be 32 plus 1, so 33 over 4. So now we know our time period is 33 over 4 hours. And so we would plug this in, and this is all calculator, and you don't have to have a graphing calculator to do this. Our new population of bacteria would be 1,000 times 2 raised to the 33 over 4. So make sure you have your exponent of 33 over 4. And so that's going to end up being, once you type that in your calculators, you're going to have approximately, because we are rounding this, 304,437 bacteria. Somebody needs some antibiotics. Okay, so now for the next part, it asks us to determine mathematically, as if we would do anything else, when the number of bacteria will be 1 million. So now they're giving us a population of 1 million, and they want to know, well, after how many years will this happen? So here we're going to take our equation again. Our population is 1,000 times 2 raised to the t power. But now that population is going to be 1 million. So, my goodness, it's an epidemic, equals 1,000 times 2 raised to the t power. And so now we need to solve for t. So now we have a reason for going through all those crazy equations that we just worked through. And so we can solve for our time frame. So 2 raised to the t power equals, and let's chop off some of those zeros, equals 1,000. And so please don't try to divide by 2. That's not what this is saying. T is our exponent. So now we're going to have to take the log of both sides. So we're going to say log 1,000 equals log 2 raised to the t power. Well, log of 1,000, 10 to what power is 1,000? That's going to be 3. Equals, and we can move our t now down to the front, so t times log 2. We need to divide both sides by log 2. And now we're going to type this in our calculators to see what we get. And if you do that, your time frame, you should get approximately 9.966 years is going to be your time frame. And don't forget your units. You need to make sure you're addressing bacteria up on the previous example and years for this last example. Okay, for our second example, it's saying that we're going to use the same bacteria as the original, but now this time we are tripling every 2 hours. So we triple every 2 hours, and how does that change the problem? Well, our initial bacteria will still be the same, so we know that is 1,000. Now the rate, we are tripling, so it's going to be at a 200%. And then in the number of time period, so every 2 hours, so again that n is going to be 2. So when we go through and write the equation that describes this growth pattern, then we're going to have the population equals 1,000 times 1 plus 2, because that's going to be our 200%. And now this time we're going to have our time, but it's divided by the number of times that we're going to happen every hour, which is going to be 2. So again, we can reduce this down to be 1,000 times 3 raised to the t over 2. And now we want to know with this type of rate, well, let's see, draw a graph that shows the bacteria present. And again, this is a growth. So this time it's going to be starting out a bit slower and growing. So here it's going to look, again, very similar to the same. We're not real interested in the graph of it, so to speak. Now for part C, how many bacteria are present after the same time frame? So let's look at the same time frame, 8 hours, 15 minutes, and we saw with the last problem, that means that my time is going to be 33 over 4. And now whenever I'm plugging into my equation, I'm going to have my initial population. So let's see, that's going to be 1,000 times 3 to the, and it's 33 over 4 divided by 2. So really that's going to end up being 1,000 times, let's simplify that down to be 1,000, and then that's going to be times 3 raised to the 33 over 8. And when you type all of that in your calculators, you should get pretty close to 92,923 bacteria. Okay, now by that same idea, we are going to now see, well, how many years would it take for us to get 1 million bacteria? Why we would want 1 million bacteria, I don't know. And so that's going to be equal to our 1,000 times 3 raised to our time divided by 2. And again, that's going to move over and we're going to have 1,000 equals 3 to the t divided by 2. And again, we need to do the log of both sides because we're solving for our time period. And we're going to go ahead and move t over 2 to the front. So that's going to be log 3. And so log 1,000 is equal to 3 equals time over 2, log 3. And we can go ahead and multiply by the 2. So I would go ahead and do that, make it a little bit easier for us. So we have 6 equals t times log 3. And so solving for our time, it's going to be 6 divided by log 3. It's going to be our time frame. And so when we type all that in our calculators, our time should be about 12.575 years. Okay, our next example, we have the population of a town is 100,000 and it's increasing at a rate of 2.15% a year. So again, let's go ahead and set up our variables, make it a little bit easier for us. So our initial population that we were given was 100,000. And our rate at which the population is increasing was 2.15%. So as a decimal, 0.0215. And how many times are we going to use this rate? Well, it's just happening a year, so time frame would be 1. And so now we're ready to write our equation that shows our growth pattern here. So our new population is going to be equal to, again, we have 100,000 times, and we have 1 plus, this is a growth, 0.0215, and raised to our t over 1, or just t. And again, you can condense this inside the parentheses and make that 1.0215, all raised to the t power if you want to. And now again, draw a graph representing the town during the first 50 years, and we can come back to that. It's still going to look the same. Now let's look at part C. How many people are present after 10 years? So let's plug into our formula. And so our new population is going to be equal to 100,000, times, and on the inside of the parentheses, I would condense those, just make it easier, 1.0215. And now after 10 years, so I'm going to sub in 10. And after we do all that calculator work, you should end up with 123,704 people. So, well, if my pen would write, that would be so absolutely useful. Sorry, folks. All right, so now for the next part, they're going to give us a time frame. So determine mathematically when the population will have doubled. So if we started out with 100,000, if we double that, hopefully most people will get 200,000. And that's going to be equal to our 100,000 times our rate, 1.0215, raised to the t power. And again, we're going to go through and solve for t. So simplifying, go ahead and divide by 100,000. So 2 equals 1.0215 raised to the t power. You will need to take the log of both sides. So log 2 equals t times log of 1.0215. And then divide both sides by this log value so we can solve for our time frame. And yeah, type that in your calculators and let's see what we're going to get. So here, 1.0215. And so it looks like if we type that in, hopefully we will get a time frame of 32.585 years. So that's not real long for your population to double. So for our next problem, we're told that the population of Allentown, Pennsylvania was 5,000 in year 1900 and has steadily grown by 12.68% every 4 years. So let's go ahead and plug in. Our initial population is going to be 5,000. And then our rate, so let's see, we have 5,000. Our rate, 0.1268. And let's see, number of times that we're incorporating that rate 4 times, or every 4 years. And now let's write our equation. So our new population will be equal to the initial population, 5,000, times 1 plus our rate, 0.1268, raised to our time over 4. And again, you're welcome to combine those values inside the parentheses. All right, moving on past the sketching, we again know what that's probably going to look like. So let's do part C. How many people will live in Allentown in the year 2008? So we have to be careful. Again, I would write my equation to see what all values we need. We have 500,000 times 1.1268. And we need a time frame. and then we need to divide that by 4. Now we have to be careful because our time frame is not really 2008. So we have to think about, well, when did we start recording, or what was our initial time, which was 1900. So what is the time frame from 1900 to 2008? That's our t value. So hopefully we see that our t value would be 108 years. So that's what we need to plug into our formula. So our new population is going to be equal to 5,000 times 1.1268, and that's going to be raised to 108 divided by 4. And when we type that in our calculators, you should get 125,555, and that's going to be people. Okay, now let's see, part D. We need to determine when the population will reach 150,000. So let's see, let's go over here to the side and work that one out. So I'm going to do part D here. And now we are given the population, which is 150,000. And I want to know, well, how long is it going to take for us to reach that value? So that's going to be equal to our 500,000 times 1.1268, and then that's t divided by 4. And we need to divide both sides by 500,000. So I have 30 equals 1.1268 raised to the t over 4. And now we need to do the log of both sides again. Log 30 equals, and I'm going to go ahead and move my exponent down. So I have log 1.1268. Go ahead and multiply both sides by 4. And I'm going to go ahead and incorporate the other part too. After I've multiplied by 4, I will divide by log, I'm running out of room here, 1.1268, and that should give me my time frame. And hopefully, let's see, what is that going to give me for my time? So that time frame is going to be, and I'm going to move back up here since I'm running out of room. So for D, the time, if you type all that in your calculator, is going to give you 113. Now be careful, it wants to know what year. And again, our initial year that we started with was 1900, and then I'm going to add 113 to that. So it looks like 2013 is when that population is going to happen. For our next example, we have the population of a small western town in the year 1860 with 7,500 and decreasing at a rate of 3.85% every 2 years. So again, let's go ahead and identify what our variables would be. And our initial population, let's see, was, what did it tell us? 7,500. So there's our initial population. Our rate is decreasing, so that means that I have a negative rate here. It's decreasing at, and if we change that to a decimal, we're going to get 0.0385. And let's see, how many times does this happen? It is every 2 years. So now when we write our information inside of the parentheses, we're going to see that we have a minus inside here because our rate is not increasing, it is decreasing. So our, let's see, our original population, 7,500 times 1 minus 0.0385, and that's raised to the time divided by 2. Now again, here on the drawing part, this would be some kind of decay. So if we had to sketch the decay curve, do remember that decay is going to look something like this. It is decaying, right? And again, we would use our calculators for that. So part C, how many people live in the town in the year 1935? Okay, and so the first thing we need to do in part C is to see, well, what is the actual time frame? Because it's not 1935. You have to remember what year were you starting from. And so when we set up part C, again, our new population is going to be equal to 7,500 times 1 minus this time, because again, our population is decreasing. 0.03, what was the rate? 85, and it's raised to that, and we have to see, well, how many years have passed? So how many years has changed from 1860 to 1935? And if we subtract those, it looks like about 75 years is our time frame. So we would have, so my year frame would be 75 over 2. And again, just straight typing this in your calculator, it looks like I got 1,721 would be your new population. I'm sure PEEPS is an official unit of measure here. So how many people live there today? So for part D, first thing again, we need to see what is the time frame that's elapsed from 1850 to today. And so from 2018 all the way back to 1860 is 158 years. So we would set up again our population. My pen didn't want to write. Our new population is going to be 7,500 times 1 minus 0.0385 raised to the, get this slid over, raised to the 158 over 2. And so the new population for today, if you type all that in, you're going to get about 337 people. In part E, in what year was the population cut in half? So what was our original population? It was 7,500. So in what year was our population cut in half? And I'm going to try to squeeze this in between C and D, the work for that. And I'll set up the equation, and then you can go through and solve it since I'm running out of room. So part E, if the population was cut in half, what is half of 7,500? That's going to be 3,750. And so that's going to be equal to, and to finish setting this up, you're going to have 7,500 times 1 minus 0.0385, and all of that's raised to the t over 2. And so when you finish solving this, and do solve this, and you all can finish this out, your time frame would be 35.3 years. And so the year that the population was cut in half would be 35 plus 1860, so year 1895.